Hi there, and welcome back. What we're going to do is apply all of the graphical properties that we learned about for a function, increasing, decreasing, concavity, etc. And we're going to try to graph the function f of x equals 10x to the third minus 3x to the fifth. And you'll notice that I have the first and second derivatives right below it because we know we get information about a graph from the first derivative of the function and the second derivative of the function. So the key is to organize this in a way that we get everything we can from each function. So first off, we have f of x. Now f of x is where we can get the domain by looking at the expression. This one happens to be a polynomial, which means the domain is all real numbers, so negative infinity to infinity. And we can also get the intercepts of the graph, which are nice key points when they're convenient to get. So remember that the y-intercept is the point where x is equal to 0, and we get the point 0, 0. Our x-intercepts are the points where f of x is equal to 0. So we set that equal to 0 and we solve. So factor out x to the third and then set each factor equal to 0. We get x equals 0 again, and we get x squared equals 10 thirds, which means x is equal to plus or minus the square root of 10 thirds, which I'm just going to leave unrationalized right now because we're just going to approximate it later when we get to the graph. So basically what we know is, so far, the domain is all real numbers and we have 3 x-intercepts. And one of the x-intercepts also happens to be the y-intercept. So not a lot to go on. Let's look at the first derivative. So here's our first derivative. And we set it equal to 0. Normally we would also look for undefined, but we don't have any values of x where this is undefined. It's a polynomial. So we factor again, and we still get 15x squared equals 0 over here, which means x equals 0. That x equals 0 keeps coming up. And the other factor, 2 minus x squared equals to 0, means x squared equals 2. Which means x is equal to plus or minus the square root of 2. Now, for testing purposes, for the first derivative test, I always like to get an approximation of any real number I might not really know the value of, and we know square root of 2 is about 1.41. So that means when it comes to test numbers around the square root of 2, I would use 1 and 2 on the positive side, and negative 1 and negative 2 possibly on the negative side. As you can see here, those are the exact test numbers that were selected here. And notice the intervals, that's on this line right here, the intervals that we're testing, negative infinity to negative root 2, negative root 2 to 0, 0 to root 2 to infinity, and again, selecting numbers that are inside each of those intervals that are convenient to substitute into the first derivative. So down here, we substituted each of those test numbers into the first derivative. Negative values mean negative slopes, mean the function is decreasing. Positive values mean positive slope, which means the function is increasing. And as you can see from the arrows I drew there, it's decreasing on the first interval, then increasing yet again, and then decreasing. So what this means is it's increasing, the function f of x is increasing on the open intervals, negative root 2 to 0 and 0 to root 2, as you see in the middle there. And it's decreasing on the other two intervals, negative infinity to negative 2 and root 2 to infinity. Which then means there is a local min at x equals negative root 2, and I just wrote negative root 2 comma f of negative root 2. We will figure out that coordinate when we need to when we graph. And there's a local maximum when x equals root 2, which means the point root 2 comma f of root 2. Okay, so we're just kind of collecting all this information. Now we have a little bit more. We know that there's a min point and a max point, and we know which direction the graph has to go in between those min and max points. Great. But there's still a little bit more we need to know. We need to know a little bit more about concavity. So we go to the second derivative, and that is right here. So take our second derivative, set it equal to 0, again ignoring undefined, factor out 60x, and we get x equals 0 and x equals plus or minus 1. So now we have 3 possible transition points as far as concavity goes. So we make our second derivative number line, again keeping in mind the intervals, negative infinity to negative 1, negative 1 to 0, 0 to 1, 1 to infinity. And what we notice is when we plug in our test values, and you notice I substituted plus and minus 2 and also plus or minus a half. There's nothing sacred about those values, but again, trying to keep it convenient. Substitute each of those values in, and at negative 2, we get a positive value, which means concave up, since it's the second derivative. So I'm just going to write in here, it's up here, down here, up here, and down here. So let's write our open intervals for the concavity direction. It's concave up on the interval, negative infinity to negative 1, joined with 0 to 1. The function is concave down on the interval negative 1 to 0, joined with 1 to infinity. And we have 3 transition points for the concavity. It goes from up to down at x equals negative 1. So we'll say negative 1, f of negative 1, 0, f of 0, which we do technically already know that point, and 1, f of 1. So now we put this all together. We can plot the 3 points of inflection, we can plot the intercepts, we can plot the mins and maxes, and pay particular attention to which way the graph is moving, increasing, decreasing with concavity. When we do so, here is the graph of the function. So let's just examine everything here. So these 2 points right here, the 2x intercepts on the outskirts here, we have plus and minus 1.826. That is your square root of 10 thirds. Okay, so really, this is square root of 10 thirds, comma 0, or the rationalized form. Okay, the min and max, now notice the x coordinates are plus and minus 1.414, which is your approximation for the square root of 2. So that definitely lines up with what we found. When x equals negative 1 and when x equals 1, we have our points of inflection, and that is definitely apparent on the graph. At 1, 7, you notice it's opening upward to the left and opening downward to the right, and vice versa at negative 1, negative 7. And we have our other x-intercept 0, 0, which also happened to be a point of inflection. So there's our 3 inflection points, and remember all of the details that we found. It's increasing from negative root 2 to 0 and then 0 to root 2. So on this part of the graph, so increasing and concave down has that shape that we see here. And increasing and concave up has this shape here. And then it switches to concave down for the rest of the road to the right. And to the left of negative 1, negative 7, you notice the graph is always concave up. So all of the things that we found definitely are confirmed with this graph. And there we have it.